Yeah. So on behalf of Manipal Center for Natural Sciences, I welcome all the participants for this Science Day celebration talks. I am very happy to invite Professor G.C. Anupama to talk on 30-meter telescope. A 30-meter telescope is one of the important mega science program in India. This project is an international collaborations, and then many countries are participating. The three main research institutes which are actively involved for this mega project are IRIS Nainital, IIA Bangalore, and IUCA Pune. So some generic features of mega science project has been discussed in our previous science day lectures from DST, and we came to know their benefits, challenges, multi-agency involvements, and role of leading institutions. This project need involvement of large number of scientists, engineers, and technical managers. Today, we will learn about this TMT project in detail from Professor Anupama, who is the core center. Professor Anupama did her PhD in astronomy from Indian Institute of Astrophysics. Now she is a senior professor positions. She was the president of Astronomical Society of India. She was the dean IIA, and she is the PI of Growth India project from Indian side, which is a global network for telescopes for study the transient. And she was the member of Finance Committee of International Astronomical Union, and she was the member of Commission 19 of the International Union of Pure and Applied Physics. She received many prestigious awards like C.V. Raman Young Scientist Award for the year 2001. She is the Fellow National Academy of Sciences. She is the Fellow of Indian Academy of Sciences. She worked as an editor, Bulletin Astronomical Society of India. Her research interest is mainly on novae and supernovae. And she also studied electromagnetic follow-up of gravitational wave sources, activity in development of astronomical facilities. She has more than 200 publications and 7 PhD students. Today, her talk title is 30-meter telescope and India in its development. I would like to request Professor Anupama for her presentation. We have a hybrid audience here. We have our local MCNS people in the auditorium, as well as we are streaming it in YouTube, as well as online participants are there. So we are eagerly waiting for your talk. So Professor Anupama, over to you.
Thank you. Good evening to all. It's my pleasure to be a part of your National Science Day celebrations, and also, give you a glimpse of the 30-meter telescope project. So let me just share my screen and okay. So I hope you're seeing the presentation now.
Yes, yes.
Yeah, okay. So as I said earlier, and as was also mentioned, I'll be talking about the 30-meter telescope and also the India's role in the development of this mega project. So before I go to actually talking about the telescope itself, let me just give a brief introduction to astronomical observatories, what they consist of. Basically, astronomical observatories consist of telescopes, and these telescopes can be across the entire electromagnetic spectrum, in the radio region, the infrared, optical, and ultraviolet, which use mirrors. We also have telescopes in the X-rays and gamma rays, which use special mirrors, and high energy gamma rays, which basically study the Cherenkov radiation in the atmosphere. So the basic utility of a telescope is to collect the radiation from the celestial sources. And there are instruments associated with the telescope which actually analyze the radiation that is collected. The analysis is of the intensity and the polarization of the radiation that is received, or to study the spectrum. All this gives us information about the physical conditions of the celestial sources. And of course, at the back end of the instruments, to actually record what is received, we need to have detectors. By and large, observatories are located at remote sites and they're located at high altitudes. And why is this? This is basically to avoid man-made pollution, like the light in the case of optical telescopes, and to avoid, in the recent times, the radio interference in case of radio telescopes. Just to give you a brief recap on the telescope, as I said earlier, the telescope is a light collector. So it is a combination of mirrors. So we have a primary mirror, which is what decides the size of a telescope, which receives the parallel rays which are coming from the celestial sources. And these rays, actually they focus at the prime focus, but generally just before the prime focus, there is a secondary mirror which will reflect the light onto a focus point. Now this focus point can actually be behind the primary mirror, or we can have another mirror, a tertiary mirror, which will focus the light to the side of the telescope, which is called as the Nasmyth focus. When the focus is behind the primary mirror, we call this as a Cassegrain focus. The most common optical design for telescopes is what is called as a Ritchey-Grating design, which consists of a hyperboloid primary and a hyperboloid secondary. And this is a preferred design because this is free of several aberrations due to the optics. And it also gives a nearly flat focal plane, which makes it very easy to have the instruments and the detectors located, and you can get a uniform focus across the field of view. So basically, what a telescope does is it increases the apparent angular size of the distant object, that is, magnifies them. And it's as I said earlier, it's a combination of optics, which can be a combination of lenses or a combination of mirrors. All modern day telescopes are reflecting telescopes, that is, it is a combination of mirrors. So the larger the aperture, obviously, the more is the light gathering power. In fact, the light gathering power goes as the square of the diameter. And also, the larger the aperture, the better is the resolving power of a telescope. This is the simple equation coming from the Rayleigh criteria. It goes as 1.22 times wavelength by the diameter. So you see that the larger is the diameter, the better is the resolving power, that is the angle separation between two objects. The celestial sources. Then you have spectrometers, which give spectral information, which tells us a lot about the physical conditions of these objects. Or you have polarimeters to study the polarization state of the radiation we receive. If one is interested in high spatial resolution, then one can have interferometers, and also use coronagraphs, where you block the source, the light coming from the central bright source, and which will help us detect faint features or sources around bright objects, like for example, planets around a star. These are the basic instruments, and of course, these are generic instruments, and one uses variants of these above generic instruments for the various types of studies that we would like to do. So to give you a brief history of optical telescopes, it was in the year 1609 that Galileo first used a telescope for doing astronomy. And then we had in 1610, Kepler used it. And these are some of the landmark events in the history of optical telescopes. The first somewhat large size telescope was in the year 1897, the 1 meter refractor telescope at the Yerkes Observatory. A very This telescope brought out a lot of important science. The next major development was with the development of the 5 meter reflector at Mount Palomar in the year 1948. This telescope is still in use. The 6 meter altazimuth telescope at Zelenchuk in 1976. And the 1990s saw a large number of 6.5 meter to 10 meter class telescopes. So basically, with the progress in technology, there has been a significant amount of progress in the size of the telescope, as well as in its control systems and overall the efficiency of the telescopes. So scientific advancement is always correlated with technological process, as well as technological process is in turn correlated with the scientific advancement. It's a wonderful handshake between science and technology. So what this technological progress as well as the scientific advancement gave us was an increase in the light gathering power and an increase in the resolving power of telescopes. It led to the development of active and adaptive optics, led to combining of light or interferometry using 2 or more number of telescopes, which has improved the spatial resolution of the objects that one observes. So today the largest telescopes are the 10 meter class telescopes, but the future lies in the 20 to 30 meter class telescopes, which will be coming in the next decade or so. So let me just very briefly talk about the present ground-based telescopes in India. I'll be concentrating only on the optical infrared telescopes. We have several 1 to 2 meter class telescopes and a 4 meter class telescope, that is a 3.6 meter Daviston optical telescope, which was recently installed in the year 2017. So in fact, the largest telescope we have in the country today is this 3.6 meter telescope. Just keep in mind that I told you in the previous slide that the largest telescopes available in the world today are 10 meter class telescopes. And in 1948, we already had a 5 meter telescope, the Palomar 5 meter telescope. But unfortunately in India, it is only now that we have a 4 meter telescope. But of course, I mean, we are overcoming this deficiency with our participation in the future giant segmented telescopes. These are the 20 to 30 meter class telescopes. There are 3 such telescopes which are coming up. The European Large Telescope, which is a 39 meter diameter telescope. The Giant Magellan Telescope, which is a 25.4 meter diameter telescope. And the 30 meter telescope, as the name suggests, it's a 30 meter diameter telescope. The European Large Telescope and the Giant Magellan Telescopes are going to be located in Chile in the southern hemisphere, whereas the 30 meter telescope will be the only large optical infrared telescope which will be located in the northern hemisphere. And that's very important because otherwise we would be losing out the study of a lot of interesting objects in the northern hemisphere. All these three telescopes are segmented mirror telescopes. What this means is that the primary is not a single mirror, but it consists of several mirrors in form of, it's segmented. There is a basic difference between the ELT and the 30-meter telescope and the Giant Magellan telescope. The Giant Magellan telescope basically consists of 7 segments. Each segment is 8-meter diameter. So as you can see in this artist rendition, these are the 7 segments, central and the 6 outer segments. Each of them is of 8-meter diameter. On the other hand, the ELT and the 30-meter telescope consist of hundreds of hexagonal segments. Each segment is about 1.4 meter across the corner. So although all three are segmented telescopes, there is a basic difference in the design of these telescopes. So let me come to the 30-meter telescope and give you more details about that. So the 30-meter telescope is a partnership. It's an international partnership consisting of CalTech and the universities of California, with generous funding by the Gordon and Betty Moore Foundation. Aura from the US is also a partner, currently as an observer in the project. The other partners are Canada, Japan, China, and India. As was already mentioned, the 3 main institutes from India are the Indian Institute of Astrophysics, Bangalore, the Inter-University Centre for Astronomy and Astrophysics, IUCA, Pune, and ARIES, that's the Aryabhatta Research Institute for Observational Sciences, ARIES in Nainital. The funding agencies are the Department of Science and Technology and the Department of Atomic Energy. So to give you an overview of the telescope will be a wide field, alt-azimuth mount, Ritchie Grating design telescope. As I said earlier, the primary is a 30-meter diameter primary, consisting of 492 hexagonal segments, each segment 1.44 meter across the corners. At the beginning, during first light, it will have an active secondary mirror, but not an adaptive secondary. It will consist of a flat tertiary mirror, which will beam the light to the Nasmyth focus, that is to the side of the telescope tube. And up to 8 instruments will be available over the 2 Nasmyth platforms. So you can have 2 Nasmyth platforms on either side of the telescope, and totally 8 instruments will be available. And together, these instruments will cover all the way from the visible to the mid-infrared wavelengths. And also, right from first light, the adaptive optics system will be in place, which will enable obtaining diffraction-limited images in the J, H, and K bands, that is in the near-infrared region, from 1 micron to 2.5 micron. And this adaptive optics system will be able to feed 3 instruments in the near-infrared region. So what is adaptive optics? The Earth's atmosphere is not very stable, it is turbulent. And this turbulence causes the image to blur in this manner. Okay. So actually, if you're looking at a star, the star is at infinity more or less. And so it should just appear as a point source. But on the other hand, it will have a definitive size because of this blurring, which is happening due to the Earth's atmospheric turbulence. And this measure of the turbulence is called as scene. So the best sites will have, the lower the value of the scene, the better is the site. So the best sites have about 1 arcsecond image scene, And the goal of the adaptive optics is to measure this turbulence and correct for the wavefront errors which are caused by this turbulence. So basically what is happening is that the light, if it had been a flat atmosphere, all the light coming would come and get focused exactly at the same point at the same time. But because of the turbulence, you have this sort of a waviness, as a result of which it will not get focused at exactly the same position at the same time, and that causes this kind of blurring. This turbulence is happening over extremely short time scales. So when we actually are integrating, we're integrating for something like a second or so, whereas the turbulence is happening over timescales of milliseconds. So what we are seeing is an integrated image, which will be blurred. Okay. So this blurring is accounted for, and it is corrected for by this adaptive optics method, where you have a series of small mirrors which will constantly check the wavefront, compare it with the actual wavefront that is expected for the telescope, and apply the necessary corrections. And with that correction, you from this blurred image, you will get a nice sharp image. So essentially, one can have an adaptive optics system which will give you an image at the diffraction limit of the telescope. So the diffraction limit is approximately lambda by d if you take it that way. So at 1 micron, for a 10-meter telescope, which is the current largest telescope, you can get a spatial resolution of 0.02 arcsecond. And for the 30-meter, at the same wavelength, you'll get a spatial resolution of 0.007 arcsecond. So this is the spatial resolution that you can get. Technically, you can get with an adaptive optics system with a 30-meter telescope. Another important factor to keep in mind for any telescope is the design of the dome. Because the dome itself can cause additional turbulence because of temperature differences inside the dome and outside. And this turbulence on the surface of the mirror can also blur the image. So the TMT dome is designed in the form of a caloid enclosure, which will be rotating. And this is how the slit is, and it will open up in this manner so that it's practically open almost completely on one side, the side where the telescope is pointing to the object. And on the other side, it is covered so that it will provide protection from the wind. Another important factor about this design of the dome is that for the size of the telescope, which is 30 meters, the radius of the dome is just 33 meters, which means it's a very compact dome for the 30-meter size telescope. Which also means that the cost comes down. Okay, so it's also very cost effective in addition to being scientifically very effective. Now, where is this telescope going to be located? The preferred primary site is Mauna Kea in Hawaii. But if for some reason we are unable to host this telescope at Mauna Kea, the alternate site is La Palma, which is on the Canary Islands in Spain. I'm sure many of you remember and have heard of La Palma because of the recent volcanic eruption. But the volcanic eruption is far away from the actual observatory. So what are the top level requirements from the science that one wants to do with the telescope? The telescope should have a wavelength range of all the way from 0.31 to 28 microns, that is all the way from the ground UV to mid-infrared region, with a field of view of 20 arc minute diameter, which is a fairly wide field of view for a 30-meter diameter telescope. It should have an observing zenith angle range of 1 degree to 65 degrees, have an extremely good pointing to better than 1 arcsecond RMS, and it should be able to feed any one of the several science instruments just by rotating the tertiary mirror, which essentially means that all the 8 instruments will be available for observation on any given night. One does not have to remove one instrument and put in another, so all 8 instruments will be available. And just by rotating the tertiary mirror, one can use any of the science instrument of interest. Another important requirement which will be fulfilled by this telescope is that it will slew from one science object to another and initialize the instrument and make the instrument ready for observations within 5 minutes without an instrument change, and within 10 minutes when there is an instrument change. Now, this is an extremely important factor, especially when one is looking at follow-up observations of rapidly changing objects like transients, which is a supernova explosion or a gamma ray burst, or a gravitational wave source, where you really need to move and catch it on at the very early phases. And of the 3 large telescopes, the TMT is the only telescope which has this fast slow facility. So it is ideally suited for the study of transients. So what are the instruments that are going to be available? There are a suite of instruments planned which will enable observations all the way from point 31 to the mid-infrared regime. Of these first 4 that are listed here are going to be available at first light. That is when the telescope comes online. And this is the adaptive optics system in the near infrared. And there'll be a wide field optical spectrograph, which will have a low to medium resolution spectroscopic capability, multi-object spectroscopic capability. A near-infrared imaging spectrometer, again with multi-object capability, which will be fed by the adaptive optics system, and a multi-object diffraction-limited high-resolution infrared spectrograph, which will also be fed by the adaptive optics system. So these are the 3 first light instruments, of which 2 of them will be fed by the adaptive optics system. The rest of the instruments are the ones which have been proposed as the second generation instruments. That is, the instruments which will come after the first light with a timeline of a 2 to 3 year gap. So of these several instruments that have been proposed by the community, the scientific community, which is part of the 30-meter telescope project, the high-resolution optical spectrometer has been chosen as the first of the second generation instruments which will come online. And this instrument is an India-led instrument for which the design studies are already going on. So here are some brief descriptions of the first light instrument, the IRIS or the infrared imaging spectrometer. This will give you diffraction limited images. It's an integral field spectrograph. That is, it is got a fibered bundle which will image and then take the light onto the spectrograph. It has a wavelength coverage all the way from 0.84 micron to 2.4 micron. The next instrument is the WFOS, which is a seeing limited instrument in the optical range. And as I said earlier, it will have moderate resolution spectra. It will provide moderate resolution spectra, and it enables multiplexing using slits. That is, it's a multi-object spectrograph. The third one is the adaptive optics fed, diffraction limited, multi-object, high resolution infrared spectrograph, which is operate between the 0.95 to the 2.4 micron range. So here is a top view of how the instruments will appear on the two Nasmith platforms. And here is a movie which shows how the light is deflected onto the various instruments. So you're getting the light from the primary, going to the secondary, onto the tertiary, and from there it is reflected to the instrument. As the tertiary rotates, the light can get deflected to various instruments on either side of the Nasmith platform. So you can see that the tertiary mirror is rotating and the light is getting on to a different instrument each time. So let's talk about a few science cases that can be done with this, that we plan to do with this telescope. There are a lot of science cases, of course, which can be taken up, but I'll just concentrate on a few interesting ones. In the year 2015, the community had a very detailed look at the science cases, updated the science cases that one would like to do with the telescope. And the main areas of interest are in the areas of fundamental physics and cosmology, the study of the early universe and the galaxy and star formation, the studies of supermassive black holes, nearby galaxies, and of course the Milky Way. Star formation and studying the properties of exoplanets, time domain science, and of course we cannot forget the studies of solar system objects. So it's an observatory class telescope, which means that it can do a variety of science. So obviously you have a variety of topics that people plan to use a telescope for. But some of the most interesting ones are looking at the new frontiers with the TMT in the known unknown region. So questioning, trying to find answers to questions like what is the nature of dark energy and the dark matter? Are the physical constants that we know today really constants? Are they invariant under all conditions of gravity? When were the first objects formed in the universe, the first galaxies, the first stars? How and at what epoch were they formed? A very interesting and very important question is that, is our solar system and are we unique? Are there exoplanets which harbor life? If so, what are the biosignatures? And of course, we would like to understand what are the progenitors of the most energetic transients that are observed and how are the heaviest elements in the cosmos formed. So with respect to the solar system studies, the 7 to 8 milliarc second angular resolution that the TMT will deliver, it will provide you images that are 3 to 2 times better than any of the current large telescopes. So this will help us to study the surface composition of small and distant minor planets, to get a very good temporal monitoring of the atmospheric, volcanic, and geological changes on planets, and also enable us to have a quick response to transit and unpredicted events in a solar system. So we can also study the birth of the planets. In fact, for the first time with the TMT, we will be able to study the composition of directly imaged planets by doing spectroscopy of the planets, which we can image them directly by using the method of coronagraphy, where I said you can block out the central star and not just simply detect the planet around it, but also do spectroscopic observations and study the composition of these planets. So when we study the composition of the planets, we will be able to look for biosignatures, which will tell us whether the planets are habitable or not. Now, what are the biosignatures? The biosignatures are essentially molecules of containing oxygen, for instance, or methane. These are some of the biosignatures that we can get by obtaining the spectra of the planets during what is called as a transit. So when the planet moves in front of the star, we can actually get the spectrum of the planet. And by observing the star when the planet is out of transit, we can get the spectrum of the host star. And by subtracting out the spectrum of the host star from the spectrum that we have taken during the transit, we can actually get the spectrum of the planet itself and look for the chemical composition of the planet. Another interesting science that can be done is to understand the tomography of the intergalactic medium. So as the light is from the distant source, like distant quasars, passes through the intergalactic medium, it gets absorbed by the structures in the intergalactic medium and produces these various absorption features. So the study of these absorption features, it tells you the composition of the intergalactic medium, and this will help us understand the intergalactic medium also. Of course, the unprecedented spatial resolution will allow extremely high accuracy astrometry, which will enable us to study the supermassive black hole at the galactic center and also the physics of extreme gravity very close to the supermassive black hole. We'll remember that in the year 2020, the Nobel Prize in Physics was shared by 3 people, of which 2 of the people got the Nobel Prize for the discovery of the supermassive black hole in the center of our own galaxy. And this was done through decades of studies of the motion of the stars around the center of our galaxy, as can be seen in this movie here. The stars, as they orbited around the center, as they got closer to the center, you see that they moved much faster. Right? Now, how do we study the motion of stars? By actually studying their position at different points of time. And how will the TMT help us? Here is the actual image obtained with the 10-meter Keck telescope with adaptive optics. Now, this is where the center of the galaxy is located, and the motion of these stars around the center of the galaxy enabled them to make an estimate of the mass of the central black hole, which they found to be supermassive. Now, what will the TMT do? It will provide at much higher angular resolution, and also will be able to see the fainter stars much better resolved. Like, for instance, you see this star here, it appears like a bright single star and a faint star. But with the resolution of the TMT, we will actually be able to resolve them, and these will turn out to be at 4 stars instead of just 2 stars. Of course, this is not an actual image from the 30-meter telescope because it's not there. This is a computer simulation of what the 30-meter telescope will be able to see with adaptive optics. And another interesting aspect is to study the mergers of neutron stars. As we all know that the merger of neutron stars gave rise to gravitational waves, and this has already been detected. The single gravitational wave detection which was observed in the electromagnetic regime turned out to be a neutron star merger. And it is when these neutron stars merge that they make the heaviest elements in the cosmos. Today we have just one such example, but with the facility like the 30-meter telescope, we'll be able to observe an object like what we have with the single object that we have observed and for which we have information today. That was in a nearby galaxy, but we will, with the 30-meter telescope, will be able to observe several of such mergers in the most distant galaxies. So let us come to the making of the TMT. Who is doing what and how is the telescope being built? So all the partners are contributing to the making of the hardware of the telescope, the various subsystems of the telescope. And this slide here shows the various subsystems that each of the partner is building and contributing to the making of the telescope. Let's just concentrate on what India is doing. India will be delivering the entire control system for the primary mirror. Part of the control software, the telescope control software as well as the observatory control software, will be delivering polished segments, a fraction of the polished segments. India is contributing significantly in the making of the instruments, and India will also be delivering the coating chambers, that is the vacuum coating chambers which are used to coat the mirror with a layer of silver and a protective layer, which is what makes the telescope mirrors reflective. The science instrument, that was the main telescope, the science instrument itself, practically all the partners are involved in some aspect of the other in the making of the science instruments. And India is contributing to the first light instruments as well as to the second generation instrument. So a little more on what India is doing. When we joined the partnership, it was decided that we will take up those work packages for which we could get the kind of technology which would directly help our own projects, like building a 10 to 12 meter class telescope in the country. And we did not have, or still do not fully have, the technology for developing a segmented mirror telescope. But today, with our participation in the 30-meter telescope, we have gained a lot of technology with which we can build our own 10 to 12 meter class telescope. So when we joined the project, when we began talking to the 30-meter telescope project in around 2007, 2008, we decided to take up those work packages which would help us build our own telescope in the future, to get technology which we did not have at that point of time. So the work packages that we have taken up are polishing the primary segments. Polishing of large optics is something which is very important. The M1 control systems, which include the actuators, the edge sensors, and the electronics. The segment support assembly. Each segment has its own support assembly, so we will be producing them. The mirror coating chambers, the control software, and instrument development. So this is the M1 and the M1 control systems that we are delivering. As I said earlier, we'll be delivering a part of the polished segments, about 84. India will be delivering all the segment support systems, that is 492 plus for the 82 spare segments, all the edge sensors that are required, and all the actuators that are required. I'll be explaining briefly about what each of these components are. So the primary mirror consists of 492 plus 82 spares. And these 82 spares are because these 492 mirrors are not all of the same shape. There are 82 different types, because you have to, this has to take the hyperboloid shape of a 30 meter, which has a radius of curvature of about 62 meters. So obviously the The segments are not going to, all of them, not going to have the same optical design. There's slight difference between them, but they all have to work together to behave like a single 30-meter telescope of the required shape. So each of these segments are aspheric segments, and India will be polishing some of the most aspheric segments in the outer regions, colored yellow in this diagram here. So the technique that will be used for polishing is what is called as a stress mirror polishing technique, which was used for polishing the segments of the Keck telescopes, that is a 10-meter Keck telescopes, as well as this polishing the segments of the JWST telescope, which was very recently launched, the 6-meter space telescope. So what, and the main advantage of this stress mirror polishing is that because it is using a large tool, which is almost the size of the mirror that is being polished, the material removal rate is higher. And so you can polish a larger number of segments in a given time. With the conventional way of polishing, if we have to polish a 1.5 meter a mirror, it takes roughly a year or so. If you have to now polish 500 mirrors, you cannot wait for 500 mirrors. So the target is that in 4 weeks' time, there will be a mirror coming out in 4 to 6 weeks' time. That is the target. And this technique of polishing, the stress mirror polishing, which was actually designed by the CalTech group for the Keck segments, is what we will be using. And this is a technique that we did not have, and we are learning this technique now. And there is no optics company in the country which can do this. So we have built our own facility at the Hoskote Crest campus of the Indian Institute of Astrophysics. The facility is ready. The machines will be coming in about a year's time. And this facility for production of large optics will be a large national facility which will have use beyond the 30-meter telescope project. This facility can be used for building our own telescope and not just for astronomy, for space application also. So currently there's a lot of work going on. We are learning the technique of the stress mirror polishing. We will actually be polishing a roundel, and after it has been polished to a certain level, the roundel will be made into hexagons, mounted on its segment support system, and then the final polishing will be done using the iron beam finishing. So we will be polishing the roundels, hexing them or cutting them into hexagonal size, mounting them on the segment support assembly, and then delivering it to the project. So the process for the hexing is also extremely important and very critical. And this process is being developed by an optics company called Optical, which is in Bangalore. And we're also developing several metrology tools which will be required to do the metrology while the grinding and polishing process is going on. So there have been several blanks, about 18 blanks, which were delivered from Japan. The delivery of the blanks for all the segments is Japan's in-kind contribution. And we have done the inspection of all these blanks. Here is just an example of the kind of activity which is happening already in the optics fabrication facility. The other is the edge sensors, the other component that we are making. Now, what are these edge sensors? These are the components which will measure the gap and the height between the adjacent segments. So this gap and height between the adjacent segments will be related to the actuators. And if it is not what it should ideally be, the actuators will sense this, and then the actuators will give the command to move the segment so that the relative positions come to the nominal value. So each segment will have 12 such sensors. That is 2 on each side of the hexagon. And these sensors are glass blocks. These will be made of zero-door glass. And they'll have electrodes which are formed either by photolithography or laser etching. We're currently developing the technology for laser etching. This is being done by the Institute ARCI, which is in Hyderabad. Optica is developing the glass blocks for this. Goal, the optics company, Goal in Pondicherry, had earlier developed this glass blocks. Now, each of these glass blocks are also coated with gold. So ARCI is also developing the method for coating with minimal loss of gold. The other component are the actuators. As I said, the actuators are the ones which actually give the command to position the segments. There are 3 actuators in each segment. So these take the input from the edge sensors and then they'll align the segments accordingly. The prototype actuators were manufactured here in India, and they have been very successfully tested for the functionality tests, and all of them have been very successful. The life cycle as well as the environment tests have been successful. So there are now the next version of the prototype production is happening. There are several industries in the country, in Bangalore, in Jamshedpur, and in Pune, who have been involved in the manufacture of the prototypes. The next important component in the M1 control system is the segment support assembly. So here is a segment support assembly, and you see this is the mirror. This is actually placed upside down currently, but on the telescope the mirror will be facing up. This picture is showing you how the segment support assembly looks like. It's a very complicated system. It consists of almost 500 odd parts in it. And this is the moving frame, which is the most complicated of the components in this. And these are the rods, what are called as the flexure rods, which make this segment support system to the mirror. So what this does is the segment is supported on this, and this provides a passive support to the mirror, and it also enables an active control to correct for the wavefront, the shape error. Because when the mirrors are on the telescope, there'll be effects of the gravity, and depending on where the telescope is pointing, the effect of the gravity will cause a slight change in the shape of the mirror. And so it will have to be corrected, and that is done using the segment support assemblies. So it's a combination of the edge sensor, the actuator, and the segment support assembly. All of them together will keep the telescope mirror aligned to its required shape. So once again, there are several industries which are participating. Currently, Larsen & Toubro is in the process of producing about 100 such segment support assemblies. The first 10 are getting manufactured. And with the initial prototype segment supports, with about 7 of them were assembled to test the entire aligning and phasing system. engineers from the India TMT project also participated in this. Coming to the vacuum coating chambers, as I said earlier, India is responsible for the design and manufacture of the vacuum coating chambers for the M1 segments as well as for the secondary and tertiary mirrors. About 6 months back, we completed the concept design for the M2 and M3 coating chamber, which is a single chamber. This was successfully completed in partnership with the company Hyundai in Bangalore. Coming to the software, the principal software system of the telescope control system has been the first phase of the preliminary design has been completed. Likewise, the development of a common software system, which is part of the observatory software, the phase 1 development has also been completed. Both these development, the preliminary design reviews were very successfully completed. Here are some examples. The Honeywell from Pune was responsible for the telescope control design, the module which was done. And ThoughtWorks from Pune again is working on the observatory control software. So the first light instrument that India is involved in is the wide field optical spectrograph. This is a cutout of how the spectrograph will look like, and as you can see, all the partners are involved in various aspects of the building of this instrument. India is responsible for the calibration system, is looking at the design and studying the design of the two channels of the spectrograph. We're completely responsible for the software and the control electronics. So here are some examples of the design of the grating exchanger and the camera articulation system. That was this design was done at the by the India TMT project, and this has successfully undergone the preliminary design review. So we'll soon be manufacturing some prototypes of some very critical components for this to test the working of this design. Here is the kind of software, the framework and the design has been done, and we'll soon be working on developing the modules for the software. And the second generation instrument activity has also begun. A white paper led by India for the development and optical high resolution spectrograph was rated extremely high by the international the Project Science Advisory Committee, and with the participation by from the other partners like Japan, China, and the University of California, we have begun the design studies. Here are some images showing the design, the cartoon of the design that is being developed. So to summarize, the 30-meter telescope is a 3.1-meter convex, is a Ritchie-Chrétien optical design with a 30-meter hyperboloid primary. It will have a 3.1-meter convex hyperboloidal secondary and a flat tertiary, which is 2.5 by 3.5 meter. It's very interesting to note that the smallest optics of this telescope, 3.5 meter, is actually the largest telescope we have in the country. And another interesting fact to be noted is that the instruments are as large as this 3.6 meter telescope. For example, the wide field optical spectrograph that we are working on, when built, will actually be like a 4-meter telescope, the size of a 4-meter telescope. A 20 Archimedes wide field of view actually in physical size corresponds to a 2.6 meter diameter. So it is really huge. So you can imagine the size of the instruments. It will have to take a field, it will have to take a beam of 2 meter diameter at least, right? So that is what makes the instruments also much larger. So just once again to show how the telescope structure is, you have the primary, the segmented primary, the secondary here, and at the top end of the secondary you'll have the laser launch system, which will help in the adaptive optics, where the laser is beamed on to the upper atmospheric layer of the Earth, and it is reflected back. And by looking at the images from the laser, you will know what is the aberration caused by the atmosphere, and by correcting for that, you will get a corrected image of the celestial source. These are the two Nasmith platforms where the various instruments will be located. So to summarize, the telescope will have 10 times the resolution of the Hubble Space Telescope and 5 times that of the JWST, the 6 meter JWST. An important factor to be noted here is that the space telescopes are not affected by the Earth's atmosphere. So essentially, when you have a telescope in space, you can get an image up to the diffraction limit of the telescope. This, the 30 meter telescope will also have 100 times sensitivity with the use of the high adaptive optics, high performance adaptive optics system. It will have a milli-arcsecond angular resolution, which essentially means that we'll be able to resolve objects as small as 25 kilometers in size on the Jupiter's surface. It will have an extremely high astrometric precision of 30 microarcsecond. So potentially the 30 meter telescope will be 14 times to 400 times more sensitive than the current 8 to 10 meter class telescopes that we have. So what this translates to is that it will be at least 14 times faster than, 14 times more efficient than the current 10 meter class telescopes, which means that 20 nights on the 30 meter telescope will be equivalent to at least 280 nights on the current 10 meter class telescopes. Now, why am I saying 20 nights? Because 20 nights is equivalent to the 10%, roughly 10% partnership that India has on the telescope. So we should be getting something of the order of 20 nights in a year, equivalent to 20 nights in a year. But that is like almost a year of observations on a 10 meter class telescope. So, this gives you the kind of efficiency with which you can observe and the kind of science that you can do with this telescope. So when is the telescope expected to go online? The first light is expected in 2033. The site, as I mentioned, is preferred site is Mauna Kea. The partners are from USA. You have CalTech, University of California, Universities of California, and we are expecting NSF to also come in. We have Canada, Japan, India, and China. So of course, it's an extremely challenging climb for India. The technological capabilities, a challenge in that, and of course the human, the financial resources. So today we had, in the 1980s, we had a 2.3 meter telescope, the Venuboppu telescope, which was the largest telescope in India and in Asia, until the 3.6 meter telescope, which came online in 2017. So from the 3.6 meter telescope that we have today, we will be moving to the 30 meter telescope. So when that comes online, we'll no doubt have access to the best. It's an extremely great opportunity which is bringing in a huge amount of technology. But if you look at the way the world has progressed in building telescopes, they went all the way from the 1-meter telescopes to the 5-meter telescope in the 40s. That's 1950s to the 1980s. They had they built 4 to 6 meter class telescopes, followed by the 8 to 10 meter class telescopes in the 1990s. But we are practically jumping from the 2.3 meter telescope that we indigenously built to the 30-meter telescope, right? So this is what we are jumping to. So there is a huge gap that we need to bridge. The gap in the technology, we are bridging that by partnering and making several subsystems. But the gap in the telescope size itself, from the 4-meter to the 30-meter, is a huge gap. So what we actually require in the country is a 10 to 12-meter class telescope, and we hope we will be able to do that with the technology that we are gaining, the experience that we are gaining by being partners in the 30-meter telescope. Today, we are in a position to design a 10 to 12-meter class telescope. And in fact, we have proposed a telescope of a 12-meter telescope to be built in the country, located at the high altitude site that we have at Hamle. So with this, thank you. I'm ready to take questions.
Thanks very much for this beautiful talk. And we have learned today that how this project is going on, and how our Indian participants are doing their hard work. So I'll take some here. We have mixed audience. We are not all from the astronomy background. So we'll take some questions for you, and then we'll go for online questions.
Sure.
Your talk is excellent, madam, and contribution to the telescope making hardware and software is really excellent contribution, and it will give back to the country. 10 to 12 meter telescope you are saying is really very nice to know. My question is not very relevant to your talk. In the beginning, you showed one slide in which you said, your observational astronomy can throw some light on the H cross and C. Are you talking about H cross and C time dependence, epoch dependent?
Sorry, I didn't get your question.
Universal constants will be epoch dependent. How you will make it from observational astronomy? You said universal constants are you can make out. That's what. Because when you make from Big Bang, you come to quark gluon plasma and hadronization. They are also taking same H cross and C values.
So it's basically trying to look at some of these fine structure constants. Okay, so what you do is you need to have extremely high resolution spectra of some of the distant objects. Okay, so this like if you're looking at the quasars, for instance, and you look at the in the high resolution mode, at extremely high resolution, you're looking at variability there at very precisely the slight shift in the wavelength. Okay, so that will tell us about whether these constants are really constant. So today we are able to do up to a certain level, but then the errors are so high that it can be a constant or it can be a variable.
So it is not about H cross and C, but it is about the electroweak and separation, the high structure constant you are talking about.
Exactly, yes.
Yes, thank you very much. And another question is not again related to your work. You said dark matter candidates and dark energy your the telescope can throw light, because electromagnetic spectrum does not interact with these two candidates. That's what I am very interested.
Yeah, there are indirect ways of measuring this. Okay, for example, dark matter will have some kind of a gravitational force and an effect, right? So that is something that we can measure, and there are several ways of estimating the presence, the amount of the mass of the dark matter around galaxies and all that, which is being done. So if, for example, dark matter is in the form of a small black hole, like a stellar mass black hole, we will be able to see its effect on the nearby objects when we study the radial velocities of these objects, when we study the movement of these objects. And for that, some of these studies you will need very high precision astrometry. What is astrometry? Is looking at the position of these objects. And when you're looking at the position, after a gap of let's say 6 months, there might be minor shifts in the position because of the effect of gravity. So some of these things can tell you that yes, there is an object with a mass of some mass, but we are not able to see it. So that is what dark matter is all about. Okay.
Thank you. We understood.
Yeah.
So yeah.
Good evening, Dr. Anupama. This is Prithviraj here. You mentioned about this 10-meter class of telescope, which we intend to build. Have we already made the plans, and then are there certain preliminary groups which have been constituted to work on it? And
yes.
When is it likely to come up, but all if it's going to come up?
Okay. Yeah. So have we made plans? Yes, we have made plans. We have been making plans for decades, I should say. But anyway, I mean, all large projects go on for decades. So in fact, it is with the plans that we started to make for the 10-meter telescope that we got into talking to groups, making these large 20 to 30 meter telescopes, and we were invited by all 3 projects to be part of them, and we finally chose the 30-meter telescope project because that is a project where we had guaranteed in-kind contribution. So now with our experience with the 30-meter telescope participation, today we, a couple of years back, in fact, we submitted an initial project report to the Department of Science and Technology with a basic initial concept design. Of course, we have not yet heard from DST, but irrespective of that, there's a lot of activity going on at the Indian Institute of Astrophysics. We're working on the actual design of the telescope, because it's going to be again a segmented mirror telescope. The design for this segmented primary is quite intricate. We are working that out. We're doing a lot of studies on that. We are also, developing a prototype to. It's actually a 7-segment prototype we are developing to understand how to align and keep the segments phased. And we are also looking at we are going to be looking at the telescope structure design. So there is a lot of activity that is going on. There are other institutes also participating, like TIFR is looking at some the instrument designs, particularly instruments in the infrared. So yes, there is a lot of activity going on in parallel to what we are doing with for the 30-meter telescope. But as I said, we have not yet heard from the Department of Science and Technology, and we hope we'll get some initial seed money to come up with the detailed design for the telescope and the various substructures and the dome and everything that we need.
Yeah, so we have one more question.
Hello, ma'am. Thank you for the talk, ma'am. We really enjoyed it, and we are like a few of us here are engineering students, so we are wondering how we can contribute to the project, if like however small it is. Like,
yeah, one way of contributing is that you can do projects, short-term projects with the TMT India TMT group. And in fact, we have had several project students who have come and, who have done projects and contributed significantly. And some for this 7-segment prototype that we are developing. In fact, we had a lot of BTech students who were part of the team which was designing the actuators and testing the actuators and all that. So while you're doing your engineering, also you can contribute by doing short-term projects. After you have completed engineering, also you can come and we have the project trainee positions where you can come and actually contribute to the various developmental activities. So, and of course, I mean, later on as project engineers themselves, like, so there are a lot of ways that the engineering, I mean, in fact, we do need a lot of engineers to build any telescope. So yes, these are some of the ways that you can contribute to the project. And we welcome you people to, get in touch with us.
Also, ma'am, I have one more question. You said in Hanle we are building a 12-meter telescope now. So, like, are there any like dark side protection there, because light pollution in India is also increasing? So, like, what are your views on that? Like, how is the situation of light pollution in India?
Yeah,
that's one question.
Okay, we are not yet building. We hope to build. Let me put it that way. Okay, if we get the funds, we will certainly build. But protection of dark sky, yes, that's an extremely important point that you brought out. We realize that, I mean, I can say, like, when I went to Hanle the first time, almost, more than 20 years back, it was like totally dark. There were just, we could count, there were just about 10 kind of huts, small houses in the neighboring village. Today it has grown drastically. So the light pollution is increasing there also. Of course, it's nothing compared to what we see in the cities. So what we have actually done is that we have proposed to the Ladakh UT government to declare the region around the Hanle Observatory, I think about 15 to 20 kilometer radius, as a protected region, as a dark sky sanctuary. The UT government is very positive about this, and I think we are very close to getting this done. So what this means is that, I mean, this of course doesn't mean that you cannot have people or whatever it is, but this means that the kind of lighting that will be used will have to have proper shade so that the light is directed to the ground and doesn't go up to the sky. And there will be various other factors which will be need to be implemented to maintain the dark sky quality. And in fact, this is very good because it also helps the wildlife in that region. Around Hanle, there is quite a bit of the wildlife which will be benefited by, if we declare that region as a dark sky sanctuary.
Ma'am, we have one more question.
Sure.
Hello, my question is non-technical. As you build bigger telescopes with higher accuracies, naturally the earlier telescopes, the smaller ones, do they become irrelevant in principle? Principle have to become irrelevant. Is it so?
Actually, I mean, all size telescopes are important because each one has their utility. While the larger telescopes will be used to, do some of the most cutting edge science, like you want to look at the most, distant sources at extremely high angular resolution and all that. There is a lot of groundwork that needs to be done. So the smaller telescope will provide that kind of groundwork. And, for example, if there is a supernova in our own galaxy, and it is kind of nearby, we will not be able to observe that with a large telescope because the light, there'll be so many photons that will be received by that object that these large telescopes, the detectors will be saturated. So it is the smaller telescopes which will come into picture there. And the smaller telescopes, another advantage is if you have a wide field of view, you can look at larger areas of the sky at a given time. So they are the best telescopes which can do kind of a survey kind of work. And for detection of, for example, the gravitational wave, the electromagnetic counterparts. LIGO detectors, even when you have LIGO India, for instance, they cannot pinpoint the source of the gravitational wave to an extremely high accuracy. So that is where you need these smaller telescopes with a wide field of view, which will quickly scan the entire sky and look for a new object for the electromagnetic counterpart. And once you've detected them with the smaller telescopes, you can use the larger ones to do more detailed study. So the smallest to the largest telescope will always have its utility. They'll never run out of their utility.
Thanks, ma'am, very much. So we don't have any question, but we have some online questions are there. So. So no questions, no? Online? Okay, so if anyone want to ask any question online, so they can unmute themselves. I think there is no online questions. Okay, thanks, ma'am, very much. So we are closing this for today, and we are also tomorrow we also have talks for this Science Day celebration. And Gopal Krishnan sir will talk tomorrow, and MS Valithan sir will talk tomorrow for this occasion. Thanks very much.
Thank you.